right. Hello, everybody. Welcome to Dynamic Analysis of macOS Malware using SpriteTree. Thanks for attending. Bigger crowd than I expected at 8:30 a.m., so solid. So a little bit about myself first. My name is Jaron. I'm a director at Threat Labs, working for Jamf. At Jamf, my team kind of looks into new ways to keep users safe on the macOS ecosystem. So we do everything from behavioral detections to static detections to coming up with new ways to enforce those types of things. So today what I'm going to be talking about is just a tool that we kind of built to actually help us do analysis of what's happening in the background once we detonate a sample of malware or software. System internals, we use this tool for quite a fair bit. So I'm just going to jump into kind of what it is. So SpriteTree is a tool that we built on top of SpriteKit, which is Apple's 2D graphics engine. If you've seen any of my talks in the past, you know that I put a lot of focus on incident response and threat hunting on the process tree itself. This is because the process tree can provide us with an absurd amount of information and context into what software is doing on the system. So we wanted to create an app that can assist us during analysis of what's happening on the system, mostly with malware in our case. Before we get into that and into the tool itself, I just want to start with a bit of the problem statement on macOS and why we need this tool to begin with. So the first portion of this talk could be a little bit dry because we're going to get into the details of the why, but we'll get into the usage of the tool in the second half here. So what good is a tree? Defining the reason we need a tool. To best explain that, I usually give a specific example of the etc sudoers file being modified. So the etc sudoers file is a system file that controls which users are allowed to escalate to the root user. So knowing when it's modified is probably something you might want to be aware of, but knowing that it was modified in and of itself isn't enough information. We're still missing a lot of details in terms of what actually happened here, right? If we look at the process tree, the why is often provided to us through context clues of the process tree. So, for example, here you can see that Vim was responsible for modifying the etc sudoers file. Vim, of course, a shell-based text editor that you can use to kind of modify files manually. So here, whoever modified the sudoers file did it manually via Vim. To gain even more context, we can look further up the process tree. This is a pretty common process tree that I would expect to see when the etc sudoers file gets modified with Vim, right? We see that ultimately the terminal was responsible for doing that modification. So this kind of tells us, because the terminal is a graphic, it's technically an application that you open through the graphic interface, right? Like even just looking at a tree this simple, I know that a user's probably logged into the system, they opened the terminal application, and they typed it in through Vim, right? But things change a little bit if we discover that the sudoers file was modified by Vim under SSH, right? Some power users might log into a system via SSH. It's not something that most users are going to be doing outside of maybe developers and power users and admins. And this type of tree, if I'm on, say, an accountant's computer looking at this tree, I might be a little more, what's going on here? Or how about this scenario where the sudoers file is modified via an echo command running under the Jamf daemon, right? Jamf is an MDM. One of the major services we provide is an MDM. So basically, you can run scripts across your fleets. If I saw this happen, I would probably think, okay, this was an admin. They pushed out a script to run it. This is probably just fine. However, if we expand the process tree and look at maybe other siblings of that bash shell, these also tell a story. So I can see here that netcat was run, the TCP Swiss Army knife, right? This bash instance also runs DNS_SD. This is a tool built into macOS that can look for open bonjour connections on the network. This is a little more concerning to me. I've seen attackers use this. I've seen APT actors use this command to kind of look for open SSH servers across the network, because when you enable SSH, you are now broadcasting that over Bonjour. So this looks like somebody is looking for those servers to connect to. Still, could be an admin, maybe not a big deal at all, but these are all questions we can kind of raise, an investigation we can kind of raise by just looking at the process heritage of what modified a file. So another portion of the problem statements on why trees are so difficult to build on macOS. A quick crash course on macOS process creation, or this applies to most Unix in general. Let's say that we have we've built an executable called myprogram that wants to go and get the output of, say, the whoami command. Right? At the lowest level, when you create a new process on macOS, what you're actually doing is forking your current process. Forking means you're cloning your current program, which gets you the same executable, but running with a new process ID. So that clone will then go on to run the executable we've requested, but notice it has the same PID as the clone that created it. Right, 124 in this case. So we see my program calls fork, that forked program calls exec, which then ultimately runs that whoami command. But when this runs, what we get is this, and this is because the clone created, as I said, what's called an exec, which replaces the current process space with the new executable that we've requested be run. So now, because of this, when we're collecting these process creates, these forks, these execs, when we collect them in real time and we choose to build a tree, it ends up looking like this, because one process overtook the other's PID space. Both end up having the same parent process, and therefore we get a tree that doesn't really feel like it represents what actually happened on the system. Instead, we want to build a tree with an accurate fork exec representation. This might seem like a small issue at first, but if you've done a lot of threat hunting and analysis on process trees, you'd understand the previous tree that we saw is actually pretty hard on the eyes at scale. So that's kind of one of the things we did set out to fix in our app, is to kind of make a better fork exec representation of what's occurring on the operating system. So another portion of another item that makes things difficult to understand in the macOS ecosystem is LaunchD. So LaunchD was added to the ecosystem in 2005. It's meant basically to be this ultimate scheduler that could handle the booting of system launch agents and daemons, as well as replace a lot of the various scheduling software that came with the BSD side of macOS packaged in at that time. So your things like cron, your things like at, your RC scripts, the scripty-like stuff that is kind of, there's a ton of moving pieces to it. It's all kind of plain text. LaunchD was kind of introduced back by Apple as a way to kind of replace all this and have something that's a little more straightforward and convenient. So one of the great things we got out of this change to LaunchD was the addition of launch daemons and launch agents. Basically, we as users or developers can create a plist launch agent or daemon that tells LaunchD what additional tasks to perform at startup. So here you see I've started something called some service. So you might hope that when looking at processes, there's some clear indication of the fact that some service was started by a scheduled launch daemon. So like if we're looking at the process tree, we would hope maybe we could find that out just based on the process tree alone. Sadly, there is not. If we look at a process tree at any given moment on macOS, we will see that LaunchD executed some service. We don't get to know what plist opened it. We don't get to know how it came into existence. We just know that LaunchD has a bunch of children, and among those are children of launch agents and launch daemons. In fact, LaunchD goes on to create almost all new processes on the operating system. So, for example, here you see me in Finder, and I go to my books.app application. This is kind of, once again, what we would hope that we see. We would hope that we see LaunchD, you know, open Finder, which then went on to open the Books application. But this is what we would see. And this, we would just see that Books was opened by LaunchD. So any application that the user opens is also opened by LaunchD. So basically, Finder, when you double click an application, Finder would send some type of IPC message over to LaunchD, and then LaunchD would go on to open whatever app the user clicked on. So long as, you know, permissions for that app are set according to the user that clicked it. But this, again, leaves us, if we looked at the process tree at any given moment, we would have no idea that Finder was used to open the Books application. Let's peek at one last example here just to kind of drive the point home. Let's say that a user has opened Safari and is browsing the internet, and they download an application. So they then launch that application from the Safari Downloads tab, and it opens. And of course, this is what you would think the process tree would look like. This is what we would hope for. But once again, this is what we would get. Basically, LaunchD, another message was sent from Safari to LaunchD, and LaunchD opened that application. So hopefully you understand kind of what I'm getting at. Basically, every process created on the operating system tends to have a parent process ID of 1, or LaunchD. This makes it almost pointless to actually try and build a process tree on macOS. In fact, if you're familiar with the tree command, Apple removed the tree command back after they released LaunchD, and because the tree command was essentially useless. You'd run it and you'd see that everything on the operating system has a parent of 1. So for this reason, a few years back, I created a command line application called TrueTree. You can download it from my website, themittenmac.com, where you can also download the tool I'll be talking about today. I'll include information on that later as well. But TrueTree actually performs lookups and tries to give a more accurate process tree. I know the text is small here, but we'll do better later. So TrueTree works like an enhanced kind of PS tree where it tells you what launch daemon plist cause processes to open. It also gives you network connections that are currently open by each process as well. If we go down here, we can see basically, like, here's a section of tree that kind of expands out. If you can read that, you would see that Finder is there highlighted at the top, and it went on to open Xcode. And then Finder also went on to open pages.app as well. And these both, if you looked at the process information on the system, these both would actually say they have a parent of LaunchD, right? Because of the extra context that TrueTree is grabbing, we're able to make those connections. If we scroll down a bit further, we can see that the dock at the bottom of my screen, the dock that is kind of the macOS dock, right, was responsible for opening both the Keynote application as well as opening Safari. So we're actually able to make these connections now and get an idea of what's going on. So again, that's TrueTree. That's a command line tool. It's like a one-time snapshot of your running processes, and then it connects all the dots for you. I put it together a few years back and maintain it. For those that want to, maybe use it for incident response, is where we found a lot of use out of it, and in general, just telling a better story. But the question kind of remains here: how is TrueTree actually telling what these parents are? How is TrueTree getting the lookups for what these processes, what their actual parents are? Well, there's a couple different items that I use to connect the dots with TrueTree. One of the ones that I'll put a lot of focus on here is the responsible PID. The responsible PID is one of the unique process IDs that Apple actually has on their operating system. Of course, you have a lot of Unix-based process IDs that kind of come from the BSD side into the macOS ecosystem, but the responsible PID is very specific to Apple's kind of setup, and we'll kind of dive into that here. So, responsible process ID is a macOS specific process used majorly probably for quite a few different things if you actually could see, all the source code for the operating system. But majorly, we can tell that it's responsible for determining what applications should hold specified permissions. So for example, many of us are familiar with the security and privacy controls that require applications to be approved to use the webcam, to use the microphone, record the screen, or even have access to certain files, or full disk access. Basically, you have to, when you download an app now, if your app wants to do one of these things, you have to get special permissions one time directly from the user saying, yes, I will allow this app to access my webcam, right? That's something called TCC. So for example, here you see me attempt to view the contents of a text file that's on my own desktop using the iTerm app. And despite being on my own desktop, I am denied access to doing this, right? I downloaded iTerm from the internet, I try to access a file on the desktop, it says no, you can't do that. So in order to fix this, I need to go into my settings and ensure that my iTerm has either full disk access or at least permissions to access the files on my desktop. Now we see the problem here has been resolved, but there's still a question at play. I didn't access the desktop with the terminal, or with the iTerm application, right? When I accessed a file on the desktop, I did it with cat. I ran cat went, looked at the file, and printed it. iTerm didn't do that. How did macOS know to allow this exchange? How did it know that it should allow cat to actually access that message? So watch what happens if we're monitoring processes on the system in real time and we run this cat command. Take a look at what happens here. Basically, we can see the exec event for the cat command executing. We see that it has a process ID of 25023. And we see that its responsible PID value is that of 24417. Now, if we look at this responsible PID value and we look up what this app is, we would see that it actually belongs to iTerm. So macOS sees that this cat process has a responsible process that points to iTerm, and it checks to see if iTerm is allowed to access the the desktop, and then it allows it to happen. So that's how the responsible PID is used by Apple in at least one way, and we can actually use this PID to kind of build better trees and use a lot of, like, if we look up and we see that launchd is the parent of something, we can also check the responsible PID and see if maybe we can rely on that instead, along with a handful of other PIDs. But I will say I find the responsible PID to be the most helpful because it generally points to the application, the highest level application that ran a command. Okay, so enough yapping on the problem statement. Essentially, what we wanted to do was create kind of this true tree tool, but for active running process captures instead of just a one-time snapshot of active processes. So this wasn't necessarily 100% possible, like a one-to-one exchange, because we're going to be using the endpoint security API information, and it doesn't provide all the same lookups that I can quite do if you're just running a one-time command. But in some ways, it's even more powerful if we're capturing processes in real time. So quick shout out, SpriteTree was a brainchild of 3 creators, myself and 2 friends of mine, Maggie Zernhelt and Matt Schott. They both helped me very heavily as we built this tool out together. So, like I said, we wanted to make a tool that users could perform analysis on and not have to worry about all this stuff going on in the background. A lot of endpoint security tools will provide a lot of these fields. They might not necessarily format stuff for you to make those relationship connections, but you can usually, if you're using some type of EDR or whatever, you can usually get enough of the PIDs to make these connections that SpriteTree builds for you. But we wanted to make a tool where you don't have to worry about that. We're going to format it for you and make it easier on the brain to look at all this data. So you're looking here at the SpriteTree application. It's written purely in Swift. As mentioned, it uses Apple's SpriteKit framework to display endpoint security data. So you might ask, why do we go about building something from scratch in Swift when there's a bunch of tree visualization frameworks out there already. The truth is, most of those applications are written in JavaScript and built for web UI interface, which is great. But if you're trying to build an application to do that, it's pretty tricky and a little messy to use JavaScript within applications. So instead, we were able to keep this entirely native in Swift without requiring any third-party libraries, and it was compiled nicely into one application. So not only that, but we have full control of the features we want to add in the future and get access to all the benefits that Apple's Sprite Kit provides us with, which we're not using super heavily at the moment, but at least the door is open to kind of lean into those a little harder in the future. So let's talk a bit about how it works. So first off, its primary purpose is to be able to take data captured from Apple's ESLogger tool. This is a command line tool that was added to the operating system at the start of Ventura. So you can perform a capture on any system running Ventura or later, and then load that capture into Sprite Tree. Now, I will say we're generally using this for smaller captures. In other words, we're not capturing data for weeks, right? Like, we're usually taking ESLogger, running ESLogger, taking a malware sample, and then detonating it, maybe running that for 10 minutes, and then loading that into Sprite Tree. We're using it for kind of direct analysis and not like very large captures of telemetry over the course of weeks, right? You'll probably crash the app at the moment, still working, continually working on making it better. So ESLogger, this is what you would run to kind of start capturing some stuff. You can do this on any computer, again, Ventura or later. You would just run the ESLogger command. Next, you see that we're telling ESLogger which events we're telling ESLogger to look for. These are the 4 that we currently support. We're going to add more so that you can look at some extra contextual events in the future. But right now, you can capture forks, execs, creates, and renames. If you look at the help page for ESLogger, you'll see that there's actually a ton of information that Apple will let you collect right now. We're just working on getting that accepted by the tool. File creates and renames, as well as forks and execs, which we talked about a little bit earlier. Finally, we will redirect the results of that command into a file called spriteTreeDemo.json. For every event that occurs on the operating system, you will get a rather large JSON event. So this file can get large if you're collecting for a super long time. So now we're officially recording events on the operating system. Let's just go generate some user activity, right? So first, let's go ahead and open a terminal, and then we'll just run a handful of commands. So running ifconfig to just kind of, really the goal of this is just to generate some noise at the moment. So ifconfig, maybe ping the local host, whoami commands, check processes for whatever else is going on. Again, I know that's really small, but hopefully when we get to the next section, we'll be able to zoom around and interact a little more. Next, we're going to open a new tab in that same terminal. This is just kind of to represent later, like what we're doing with the tree. But we're going to open a new tab in the terminal and start running a handful more of commands. We'll create a file in the temp directory. We'll use the move command to move a file from the temp directory to a different location. Here we're checking the man page for SSH just to generate some more noise. So now we know how to use SSH, and we'll SSH into our own local host, just for kicks. Actually, I got a reason we're doing that one, but I'll show it later. Next, I'm going to cat this Easter egg of a Lord of the Rings calendar that was just recently removed in the latest Mac OS, unfortunately. This was one of my favorite Easter eggs that came over from the BSD side as well, but that's gone. But anyway, we're catting the file. We're catting the file there, and that's kind of where we're going to stop, and we'll end our capture. So now we can take this capture that we've created, and we can load it into any system that has Sprite Tree downloaded on it. And we'll just click import JSON. So you'll see we're immediately greeted with a process tree for the events that took place. So by default, Sprite Tree is going to display this tree, based on standard parent process information, which, as mentioned previously, is not going to give us the best understanding into what's going on the system. So, for example, here you see like the terminal that we opened is just hanging out by itself. Remember what I said about how you're going to see processes with forks and execs that are confusing, and you're going to see a lot of parents like pointing directly to launch D. We see that here, where terminal has a parent process of terminal, and it's just hanging out by itself. If you looked up on the operating system what the parent of terminal was, you would see that it was terminal at the time that this was captured. So by pressing escape, we can go into the menu in Sprite Tree, and we can select a PID to build this process tree by. So we'll opt for kind of the true tree layout, like that's kind of the trust me mode, just based on the relationships that I've connected. True tree is kind of the most useful mode that I would argue exists. So this first will link forks and execs appropriately, and then it will use that responsible PID we talked about to build relationships. If the responsible PID doesn't provide any extra context, we'll fall back on the standard parent process ID. As you can see, like this builds a bit more of a less direct tree, but it makes things, we're going to walk through this and show why this is a bit cleaner and easier to understand. So one of the first things you'll notice when you open this tool is that some of the nodes have this smoky effect on them, right? And others don't. This is because we added this effect to represent a fork. So anytime you see this effect on a node, you know you're dealing with a fork and not an exec. This has the same, you see this, the process is the same. Remember, all forks are just clones, right? So you should see that ZSH has a bunch of cloned children of ZSH, which adds up. If you look at the process tree, you'll notice here that we're looking at a branch for the terminal we opened, right? First is a list of commands that were executed in the background when we opened the terminal. And then we see all the commands that we executed in the terminal itself. We'll go ahead and click on the ping node. You can notice that when we do, two things sort of happen. We get this highlighted path, making it easier on the eyes. Especially when the tree is really large. Secondly, we get a new button at the top that allows us to view the details of this node. So here we can see the arguments that were executed with this command. In this case, you probably recall one of the commands we ran was just sending a single ping to the local host. We can see that in here. And this is ESLogger captured data, right? This isn't anything that Sprite Tree is doing. This was captured by the Apple command that we ran earlier, and now we can kind of browse these nodes and look at all the commands that were run. As an analyst, you end up spending a lot of time performing these actions, right? Selecting processes, looking at the arguments they were called with. That's where a lot of time gets spent in threat hunting. So the benefit here is that we get to see it kind of in this tree. So let's scroll down really quickly to the second terminal tree. Now, up above, we see some of the basic commands we executed, but what immediately jumps out is this large bash process tree, right? Because if you recall, in our second terminal, we didn't really run any like bash scripts, at least to our knowledge. We didn't run any like SH scripts that we saw. But if we dig into this and we look into the full details of how it came into existence, right? So I'm going to go right above where all these commands were executed, click on the process. What we see, the full details here is that the bash processes do in fact belong to a shell script. This is actually due to the fact that the man command, the manual command to look up the man pages, is not a binary executable. It's actually a shell script. So when it runs, it kicks off a bash instance, and then nearly every command within that shell script launches a new process. And that's why we end up with this very large tree here from when we looked at that manual page for SSH. So that's just a quick crash course on moving around the tree and browsing the data. Now we do have a few other bonus features. For example, you may have noticed in the settings menu earlier, we do have the option to color the tree by two different PID fields, one being the process group ID, which we haven't really gotten into. We'll save it for another time, but the other is the responsible PID. So this is helpful in that it allows us to build the tree using a more logical tree layout while coloring the nodes by the responsible process ID. This is a way to think of it as a way to visualize the processes that share various macOS permissions. So for example, here you can see that all processes that ran under the terminal are this salmon type color, right? So although terminal has two large branches of commands open, we see that they all share the same responsible process ID, and therefore every command run in this terminal is operating with the same app permissions. In other words, if terminal.app has full disk access, then every command with the salmon color has it as well. This applies to everything from screen recording permissions to keyboard captures to microphone, et cetera, et cetera. This is how it was intended to be by Apple. Any way to get kind of around this would be considered an exploit of sorts, right? So for example, remember when we ran the SSH command to SSH into our own system? This was a technique we saw used by malware years back in order to gain full disk access. The malware did this because, as it turns out, when you log in over SSH, even if you log into your own local host, you actually end up generating a completely different tree under the SSH daemon, resulting in a new set of active permissions. So we've now kind of escaped the terminal here, right? You can see, in fact, that the cat command, when we catted the Lord of the Rings calendar, even though we did it within a terminal, it ends up running under the SSHD service. So this means whatever active permissions that SSH has is now what we have as someone typing in commands. So malware did this to easily gain the full disk access permission by logging into the local host over SSH. It doesn't necessarily mean if you're able to escape your current branch of tree, it doesn't necessarily mean that you've gained permissions. The really key bit here was that in order for SSH to be useful, you kind of need full disk access, right? You got to be able to move around in the terminal on the other end. So by default, Apple would provide SSH with full disk access. They fixed this by removing full disk access from SSH, and you have to manually add it yourself if you want. That's how they kind of solved this bug. But that's just kind of an example of how we can use it for also interesting analysis and maybe discovery of certain interesting vulnerabilities. All right, so let's use Sprite Tree to kind of showcase a few actual malware scenarios. So the first is a capture of the Schlayer malware. I use this as an example because it's basically a malware dropper that keeps pretty up to date and tries to evade antivirus every time it gets caught. Like the authors will go update it and try to get around whatever's catching them. It also generates a lot of system activity because it tends to be written in some type of highly scripty language. So because of this, one of the immediate things you should notice is how large the process tree it generates is. And in terms of the Schlayer malware, this sample is actually a smaller tree. I cut it off before it kind of completed its final payload execution in this case. An interesting thing that catches my attention within this capture is that most of the activity all occurs under the terminal, right? We've been seeing a lot of stuff under the terminal in our demos, but the reason I find this interesting is because terminal is usually a tool that a user intentionally uses to run commands. It's not one that gets opened in the background, right? It's not one that malware generally should use, because if you run your malware in a terminal, there's going to be a big old terminal screen right in front of the user. So oftentimes activity under terminal could be overlooked by an analyst because we might just automatically rule it as, oh, that's something the user's doing. But if we take a look at the bash instance that spawned under the terminal, we actually see why the terminal was executed. It wasn't necessarily opened manually by the user. Instead, a file called install.command was run. So a .command extension, when you use that on Mac OS, it's kind of similar as if you were to give a .sh extension. However, it will cause the script to automatically open in the terminal when double-clicked instead of being opened in, say, like a text editor or something like that. So now we know a bash script executed, and there's a lot going on in this tree, but where's the, but there's one actual feature I haven't pitched yet that's kind of a way to help focus in on data. And that's by using the timeliner we built. So we did a short capture here, but a lot of times you're capturing a lot of activity all at once, right? Especially if you're collecting file activity. So you can adjust this timeline slider down at the bottom to kind of go to a specific point in the capture. So you can see me dragging the timeline, and as we rewind the events, will disappear based on where I'm at in that timeline. Again, helpful if there's a lot going on. To watch all the tree objects, we can kind of get an idea of other branches launchd might have spawned during executed commands. So an interesting command that Schlayer uses on more than one occasion is the OpenSSL command. It uses this to actually decrypt an additional payload that came packaged within it inside of the downloaded contents. It does this doing some pretty easily reversible but still kind of sneaky techniques. So ultimately the data is retrieved and then piped into the command that you see here, which is basically taking a resting file full of encrypted bytes, and it decrypts them into a readable payload and executes that payload. So here's where the timeline actually gets pretty interesting as we drag it along. We do see some more malware commands kind of kicking off and spawning. However, we see that one of those malware commands that runs is a kill all command. Kill all takes an argument of a program name that you'd like to terminate, and it will go find all programs with that name that match, and it will, as you probably suspect, it will terminate them. So the command that the malware runs is pointed at the terminal, right? And the idea behind this is that hopefully the terminal will run a bash script and then terminate itself before the user ever really sees the terminal window occur, right? We see this all the time with scripty malware where basically you just see a little flash of, the command prompt down like in your active processes, and then it disappeared. That was something nobody ever wanted to see when you're opening different applications, but that's the same idea. That's exactly kind of what's happening here. So at this point, you might be wondering to yourself, if technically a command was run to kill the terminal process, how is it as we slide the timeline forward, we continue to see commands executing under terminal.app, right? Well, let's quickly return to where we were before. There's another command we saw run in our terminal, and this is the nohup command. So nohup basically has the ability to disconnect you from your current process tree. So this is going to take all of the arguments passed to it and run those commands under launchd. So the terminal can be killed, but this session will live on. We continue to see them spawning under the terminal process because we're using this true tree layout that's been so frequently mentioned now, right? So because we captured stuff in real time, we continue to see this according to how it's all kind of playing out. We can link back the fact that these commands that are now under launchd were originally coming from the terminal. So what are the commands that Schlayer is going to go on to execute? Well, first is the uname command, where basically we see CPU architecture is checked. This gets done by a lot of malware. Check the CPU architecture, see if it's ARM or if it's Intel on this particular Mac. According to the bash script here, if the CPU type is ARM, the malware will install Rosetta, and Rosetta is just basically a way to run kind of Intel compiled stuff on an ARM-based device. But it's going to do that all in the background at this point without the user seeing any of this, right? OpenSSL gets called again. This time it's used to decode a binary. We won't dive super far deep into that. We know this because we see the argument seems to specify an archive being passed in, then a file with the variable name bin file, resulting in the final output. Next, we see that Schlayer will clear the extended attributes from a file and give it executable permissions. Finally, we see that the decrypted binary is executed in the background with 2 ampersands, and then once it's running, the executable on disk will be deleted. So we see as we continue to drag this timeline just a little bit further, sure enough, as expected, we see the execution of the decrypted binary takes place. And what does this decrypted binary do? Well, it's going to do a lot of things in order to grab URLs it wants to reach out to. Once it has those URLs, it's going to download even more payloads, of course, using the curl command. Can't specify enough. If you're in charge or tasked with looking at your macOS environment for threats, and you're able to look at processes that are occurring across systems, learn what curl commands are normal in your environment. Curl is used by nearly every single malware that's discovered out there. A lot of developers use it too, a lot of scripts and admins use it also, but find what's normal in your environment and find out how to rule out what's normal curl activity versus what might be suspicious. This is what suspicious looks like. The good news is we can, if we're monitoring curl commands in our environments, we can see where these curl commands are reaching out to. So this is often where we just go. If we see something running this curl command, we'll probably just go grab this ourselves, in a virtual environment. We'll go download whatever we see the malware downloading, and then we'll do our own analysis on it. Yeah, ultimately what Schlayer is doing here is it's downloading a final adware family in this case, where upon installation, the authors will presumably gain some type of royalties of some type once it runs this payload that it's downloading. All right, I'm going to switch now to a live demo that focuses on a recent sample that we analyzed at Jamf from a website called meethub.gg, which is still active today, might I add. But this essentially, this came, if you look around kind of at this website and where people are seeing it online, essentially people are saying, oh, somebody invited me to be on a podcast over LinkedIn or some other medium of communication, and then when they told me the software they were using to do that podcast and I installed it, all my crypto disappeared and no software installed. So this, we went and we did a blog post on this, and I'm going to kind of walk through it with SpriteTree now. Let me just adjust here. All right, so let's walk a bit through this sample. This is just, again, same exact thing. We ran ESLogger, we performed a capture, and we grabbed, and we took that capture when we detonated the malware, and we loaded it into SpriteTree. So first what I'm going to do, again, I'm going to press escape. I'm going to go into the true tree mode, and then why not, I'll color it by responsible PID just for kicks here. First thing I also want to touch on is if we go down, we do see there's a node here. By the way, there's from some of the video captures I've been showing so far, there's been a few updates to SpriteTree, so you'll see a couple differences here. There is a node called untracked. This is for all the processes that were being created that we couldn't link to a parent because they weren't captured. In other words, if a parent belongs to a process that occurred before the capture, its parent in SpriteTree will be connected to the untracked node. So just noting that is kind of a separate fact. But here we see LaunchD. We see a lot of stuff kind of happening under LaunchD. MD worker shared. If you're familiar with the macOS ecosystem, you'll know kind of what looks normal and what doesn't. The way you learn that is by diving in and looking at these types of things, right? What jumps out to me is here I see LaunchD. I see it's running something down here called Slev. It's weird. Actually, when you download this sample, you don't download anything called Slev. You download something called meethub.gg. So here I'm going to click on this node that is Slev. Note that you see there's an additional node blinking inside of this node, right? And essentially what that is telling you is that this node also has some context information associated with it in SpriteTree as well. So if I hit open details and I look at this, I see Slev ran. That's great, but if I click context here on this side, it also tells me all the file creates and file renames that this process did. And to me, already looking at them, they're pretty interesting, right? The first one is keychain.txt. The next one is data cookies, cards.txt, passwords.txt, autofills.txt. This was not done in an environment where we, mimicked anything. We simply created a VM, we detonated the malware. This was the result. So that tells me that this malware is creating these files, and none of them look good, right? Right off the bat. So if we go up a little higher, we see where the install occurred. Here in this installer, we see that the installer is also probably creating and writing files, but we see this open command right here. And this open command, after the installer runs, one of the scripts, the package script service, goes on to execute meethub.app is what it opens. And if you noticed, while we were looking at this Slev executable, meethub is the name of the application, which we can see in the directory. The executable name is just labeled Slev for whatever reason. I still don't know the answer to why the attackers did that, but it is the case. So over here we can see a bunch of commands that were executed. Pretty interesting. If we look at them, it's a lot of recon. We can slide the timeline and kind of see what happens. I kind of hit this spot right here where the malware sort of hangs for a second and nothing else happens, right? So I can stop there and I can kind of be like, okay, well, what is this? It's OSA script. That is AppleScript, a language that is used kind of as a macro, right? If I look at that, I can see that basically what's happening here is the malware is prompting the user to enter their password, right? It's going to throw a prompt to the screen. It's going to say, hey, I need your password to perform some admin task. Please enter it. And the user's going to enter it. This happens all the time in the macOS world. And then what we actually see as we drag that timeline, right? That's right about, if you look at, that looks like it's about a 5 or 6 second window. Right about enough time to enter a password before a bunch of further commands are then carried out, right? So, and if we dive into this, again, you can read about this kind of all on our blog, but you'll see what it's actually doing is using the security command to access the password, to access your keychain. It dumps your passwords in plain text by using an additional file it installs called installer. And then it makes off with your entire keychain and all your passwords along with your crypto wallets, should you have one of the ones that it targets within its application. So that's just kind of an example of doing this analysis on a very recent and still active piece of malware. This was not Atomic Stealer, which is a big threat in the macOS world right now. This is something slightly different, but still a very interesting use case. So, Sprite Tree is available now. You can download it at the mittenmac.com/tools, and it's free. There's no charge for it. Again, you're using ESLogger and then just loading that data into Sprite Tree for visibility. More updates coming in the future. It's a free time project, so we're working on it where we can. Apply what you've learned today. What should you do? Well, experiment with ESLogger, download Sprite Tree, try it out. Just even if you don't know what you're doing, just go in, get a capture, and then follow the instructions here to just load it in and poke around. Investigate system internals is what you want to try, and you want to detonate malware in a VM in a very safe environment, right? Don't do it on your personal computer. Make sure you're in a virtual environment or safe environment to do it. Explore the process tree. You can explore the process tree and you can build detections using a lot of the relationships we saw here and a lot of the command lines you'll find within malware. This is 101 for building detections on macOS. Just find out what looks normal versus what is abnormal. Learn your EDR, learn where it records those processes and how to perform those lookups. I assure you most of them capture the right information to do that. And then finally apply those investigation skills from there. So that is it. I did not save time for questions. If you do want to come up and ask any, I will be here until they kick me out.
Yeah, because we used the entire time, if we do have questions, once he's done packing up, would you mind meeting him in the hallway? Great. Thanks, everyone.
Thank you.